Today we're going to present our work on OSSID, Online Self-Supervised Instance Detection by and for pose estimation. This is joint work by Qiao, Brian Okorn, and Dave Held from CMU. Object detection and 6D pose estimation are integral components of robot manipulation. As shown in this diagram, robots must first detect the object, estimate its pose, and then apply actions on it. However, most deep learning-based approaches require object-specific training. This means, for every object of interest, you need to collect a large dataset and train a detection network for each object. The network encodes object information into the weights and does not generalize to unseen objects. Therefore, this process needs to be repeated for every new object instance you want to detect. This incurs a heavy cost in terms of human effort, storage space, and training time. In OSSID, we propose an online and self-supervised instance detection framework. Our work is built on prior zero-shot object detection and pose estimation work. We use the zero-shot pose estimates to fine-tune a detector in a zero-shot fashion, and in turn, the object detector reduces the pose search space and makes pose estimation significantly faster and more accurate. Please note that OSSID can work with unseen objects without manual labeling. More detailed pipeline is as follows. Given the RGBD observations and the 3D object mesh model, we use the zero-shot network to detect the object and estimate its pose. Our method then converts the pose estimates to detection bounding boxes and treats them as ground truth detections with which it can fine-tune the detection network. For the zero-shot detector, we use the recently published algorithm DTOID. DTOID detects objects by first extracting features from both the object template images and the observation. It then convolves them to get similarity maps and detection bounding boxes. By changing the template used, we can change which objects are detected without retraining. For zero-shot pose estimation, we use our previous work, Zephyr. Zephyr takes a set of potential poses, compares point-wise differences for these pose hypotheses, and outputs scores for the fitness of each pose. It achieves state-of-the-art performance, yet it is not fast as it needs to search over a large pose space. In our pipeline, the pose estimates are used as a supervisory signal to the detection algorithm, but how do we select which estimates are good enough to use? We found that the pose estimation confidence scores learned by Zephyr are a strong indicator of the quality of the pose estimates. This plot shows the average pose error versus the confidence scores estimated by Zephyr. As we can see, higher confidence scores correspond to more accurate pose estimates, and we can use only these high-quality estimates to fine-tune the detector. We tested our method on two challenging datasets, line mod occlusion and YCB video. First, we show the performance of the baseline zero-shot methods, DTOID and Zephyr, on detection and pose estimation respectively. Our online self-supervised pipeline drastically outperforms the baselines in detection and achieves a slight improvement on pose estimation. As a reminder, all objects tested are not seen during training. The baseline zero-shot pose estimation had a slow inference speed because it required searching over a large pose space. However, in OSSID, the detector can crop the image, reducing the pose search space and thus greatly increasing the speed of the algorithm. As a result, compared to the Zephyr baseline, our method brings an almost 10x speed up for pose estimation. Finally, we show the detection accuracy during the progression of online self-supervised training. As you can see, there's a clear improving trend as more and more objects are correctly detected over the progression of the online training. We propose a novel pipeline for self-supervised instance detection, which uses zero-shot pose estimation to allow our detector to adapt to new objects and environments without manual labeling. The detector, in turn, dramatically increases the inference speed of our pose estimator, achieving state-of-the-art zero-shot performance on two challenging datasets. Our code is available, and we'd like to thank our sponsors and answer any questions you may have.